So far we have discussed about low Reynolds number flows through channels, pipes, these kinds of geometries. Now there are also other types of low Reynolds number flows which are very interesting, but they are kinds of flows which do not take place within a confinement, but flow across a particular body. For example, flow past a spherical body. So the classical example is that you have a sphere, you have a flow which flows past the sphere. So to make an analysis in this case, we assume that there is a sphere of radius r and fluid is flowing past it. This is very classical to one experiment which is called as Stokes experiment. So if you recall your high school physics, there is an experiment of falling sphere. So there is a sphere which is falling in a viscous oil, and when the sphere is falling in a viscous oil, there is the weight of the sphere is acting downwards, the buoyancy force is acting upwards, and viscous drag force is also acting upwards against the direction of motion. Under the action of these three forces, the sphere comes to an equilibrium, and that velocity is called as terminal velocity. And experimentally it is very interesting to measure the terminal velocity and compare the terminal velocity with a mathematical formula which is also known as Stokes law. So the objective of whatever we are going to do is to derive that Stokes law. What Stokes law you considered as a magical formula in the high school physics, we will go through step by step derivation. It is one of the very involved derivations in fluid mechanics, but at the same time very classical. So let us go through that carefully. The challenge here is the spherical nature of the geometry. Okay, it is one of the challenges, there could be several other challenges. So one of the challenges is spherical nature of the geometry. So to keep the formulation at least for the initial few steps to be geometry independent, we will use the vector form of the Navier-Stokes equation. So when we are writing Navier-Stokes equation, the first assumption that we are making that the fluid which is flowing around the sphere is a Newtonian fluid, homogeneous isotropic Newtonian fluid. Okay. Now when a sphere is stationary and fluid is flowing past it is same as fluid stationary and sphere is moving past it, because it is all about relative velocity. So this is very common in aerodynamics. In aerospace engineering, when an aircraft moves, the force on the aircraft, to calculate that, people make wind tunnel experiments where they fix the aircraft and make the wind flow past it. So it is the relative velocity that is important, not really the absolute velocity. So in that respect, in reality the fluid is maybe stationary and the sphere is moving. Here we have kept the sphere stationary and we are making the fluid move. So this velocity which the fluid is coming from a far stream is u infinity. Okay. So we will start with the Navier-Stokes equation in vector form. sometimes gravity as a body force can be included in the pressure gradient term, and this is a very common thing that we do. The reason is that you can always write P redefine P as P plus rho GH, okay, which is called as piezometric pressure, which is the pressure plus the pressure equivalent of the gravity head. So that so either way we can absorb that gravity body force term in the pressure gradient term. Here of course gravity I mean is not of much concern to us, we are just interested in the drag force. Now as I told you that because the flow is low Reynolds number, that is what we are considering. So low Reynolds number is one of the key assumptions. So the inertial terms we are neglecting. We will later on question ourselves that is it true that trivially for all low Reynolds number flows the inertial term can be set to 0, but intuitively Reynolds number is about inertia force by viscous force, therefore for low Reynolds number we can neglect inertia force, that is the intuitive way of looking into it. Now again as I mentioned you earlier that one of the challenges in dealing with this equation is that you have a pressure as an unknown, right, but you do not have a separate governing equation for pressure. So one of the key strategies is you eliminate pressure. So how do you eliminate pressure? You take curl of both sides. If you take curl of both sides you can use the vector identity that curl of gradient of a scalar is a null vector. So if you take curl of both sides then you will have this will become a null vector, okay. Now we will use this vector identity. Okay. This is a very such a common vector identity that it is inevitably used in fluid mechanics. So I warn you one thing, like when I am writing something maybe this I can reproduce easily because of my experience in teaching almost every day and over the years, but do not think it is a very special skill to memorize all this, right. This is not important, it is important to make use of this, do not try to stress yourself by memorizing these kind of expressions, but we will try to develop a good insight out of this which is more important. So one major observation is that if it is incompressible flow this term goes away, right, because for incompressible flow the divergence of the velocity vector is 0 for incompressible flow. So if it is incompressible flow, now what is this? Curl of velocity in fluid mechanics is called as vorticity. So what does it physically represent? So I am just writing this. It represents rotation in the flow, okay. So the rotational effect in the flow is related to, this represents what? This represents the viscous effect in the flow, because mu into this will represent the viscous force term in the Navier-Stokes equation. So very interestingly, see how nicely mathematics represents physics. This is a vector calculus formula which does not understand any physics, but how nicely it represents the physics, that it is relating the curl of the vorticity with the viscous force. So how is it possible? So this physically means in school level language that you have the rotational effect because of viscous interactions. Why? Imagine that you have come out or jumped out of a moving car or a moving bus. So a bus is moving and you have just jumped out of the bus. So after you have jumped out of the bus, you will see that until and unless you maintain your motion further forward till some time, you will have a tendency to topple. The reason is that when you were in the bus, you were having an inertia. When you are touching the ground, that inertia is disturbed because of the frictional resistance, which for fluid flow is viscosity. So because of that frictional resistance, there is a rotational effect that is created within itself, and that is what is making you topple. So viscosity induces rotationality in the flow. Now at least curl of rotationality, curl of the vorticity. Now so this we can write mu curl of minus sign is okay, I mean mu also you do not have to bother because mu is not 0, so the remaining thing is 0, okay. So what is the major assumption from this step to this step? It is incompressible flow, right. So load Reynolds number plus incompressible flow plus Newtonian and all those things I am not writing because Navier-Stokes itself implicates that you are considering Newtonian. So now we will use the same vector identity again, just replace V with omega. So you have right, just replace V with omega. And here you substitute omega as curl of V, and divergence of curl of a vector is also 0, right. So this is another vector identity, divergence of curl of any vector whatever is the vector. So this becomes so our governing equation boils down to, now I will just erase everything to make some space. Okay. So now take an example, do not take this example, let us take an example of a 2-dimensional flow. This is a 3-dimensional flow, right. I mean the flow may take place in a plane, but the geometry is 3-dimensional. So take an example of a 2-dimensional flow where you have only 2 velocity components u and v. this also can be boiled down to a 2-dimensional flow, because if you see the flow around the sphere, it can be perceived or simulated by the flow through a central plane where the velocity components are Vr and V theta, just the r component and theta component, there is no z component. So, if you are taking an example of a 2D flow, although the sphere by geometry is a 3D geometry, but the flow past a sphere can be very nicely modeled as a 2D flow. But the difference is that 2D flow is not in a Cartesian coordinate, or that may be described in a Cartesian coordinate system, but that is not most conveniently described in a Cartesian system, that is most conveniently described in a spherical polar system. So, here we start with an example of a 2D flow described in a Cartesian system, just to so in a Cartesian system you have the angular velocity with respect to z axis. So, z axis is this one. If you have flow in the xy plane, the angular velocity with respect to z axis or the vorticity which is double the angular velocity, so this plus this is the rate of deformation and this minus this is the rotation. Okay. So, this signifies the rotation, of course that half factor and all those things, half is if you call it angular velocity and without half if you call it vorticity. Okay. So, now the problem is that you want to solve for the velocity, but what remains as a challenge to solve for the velocity is you still have two components in this equation. To have a differential equation very comfortable, no matter how complex the differential equation is, you want a single dependent variable, right. Independent variables may be many, but dependent variable should be single. Here up to this there are two dependent variables u and v. So, you can convert this to a single independent variable by parametrizing u and v, writing the parametric forms of u and v, and that parametric form can be written by appealing to the continuity equation. So, for 2-dimensional incompressible flow you have this. So, you define this psi is a function of both x and y, which is called as stream function. So, the objective of introducing this function is to set up a parametric form of this incompressibility constraint, nothing more than that. So, if you define it in this way, then you see that this equation is automatically satisfied. So, whether this is plus, this is minus, or this is minus, this is plus, the cases are equivalent because sum total has to be 0. So, you may define this as minus and this as plus, that is also okay. So now let us put this definition here. So you can write right. So this in 2 dimensional is the Laplacian of psi. So this equation boils down to this, which becomes our governing equation in the Cartesian reference frame. In the polar system, the problem is you cannot use exactly this form because the geometry changes, you are no more using the x, y, z type of coordinate system. So in the polar system you replace this Laplacian with a new operator called as E square. I will define what is this E square, and this psi is not defined in the same way, exactly the same way as the Cartesian. This psi now has to satisfy the polar coordinate version of the continuity equation, not the Cartesian version. So this is a different stream function and this is called as Stokes stream function. So I will write the expression for E square subsequently. Of course I cannot reproduce it from my memory, so I will look into my notes and write the expression for E square. So E square okay. Okay. We will use this later on. So what are r and theta? So as you know, it is very similar to the polar coordinate system. So if you consider a plane, cut a plane, this is the polar angle theta and this is the r. So coordinate, a point here will have a coordinate r comma theta. So that r and theta we are talking about. Now a very interesting scenario is that once you know psi, you once you know what is the value of psi or what is the expression for psi at far stream, that is far away from the sphere, then that can give you a guess of what is the form of psi as you come close to the sphere. So to do that, let us understand what is the flow far away from the sphere. So far away from the sphere, how is the flow far away from the sphere? It is again parallel like this. So far away means the influence of sphere is gone. So it becomes again parallel like this. So it will be u infinity horizontal. So this u infinity will have its own components. What are the components? Vr and V theta. So, VR is what? So, this angle is 90 degree, you have vectorially resolved into VR and V theta. So, VR is u infinity cos theta and V theta is minus u infinity sin theta. Why minus is because the positive theta is actually this. Okay. So, these are at r tends to infinity. If you measure the radial coordinate from here, this is your radial coordinate at r tends to infinity, that is far away, this is what is going to happen. How this can lead to an expression for psi at r tends to infinity, that is very interesting, and we will take it up from there in the next lecture. Why it is so important is because using that form we will consider a form of psi in this equation and try to satisfy that form, and we will take it up in the next lecture. Thank you.